So let's start chapter 9, section 2, and let's talk about sequences. And I want to start with a question that is kind of a neat question. Very, very simple, but kind of neat. Let's imagine you're working in an arena or a stadium of some sort, and you have stadium seating. Stadium seating usually means that the seats kind of go up as they go back, and they tend to open up a little bit like our auditorium, and we get more and more seats per row. Well, let's imagine that the first row of our seating has 14 seats. And every row back from there, the second row literally has 2 more seats than the first row. So every time we go back a row, we get more and more seats. Well, the question would be, nice and simple, how many seats are going to be in the 10th row? Now, before we can figure that out, I guess we need to establish just a few things. First, we need to establish what this thing called arithmetic means. It's not arithmetic, it's arithmetic. The sequence is arithmetic if there's a common difference between each consecutive term. This looks so much like linear. In fact, it's pretty much exactly like linear. A linear sequence is also one where you have a consistent change in between terms. That's what arithmetic is as well. So why the need for a different word, or why the need for something, well, not linear? How are they even different? On top, I have a typical linear equation. Here's what I see. My seats start at 14 and they go up 2 per. So every time I go back a row, I gain more 2. So if I put a 10 in the X spot, which is what we would have done, well, every time before today, we would have had 2 times 10. We would have had 20 plus 14. And that would give us 34 seats in the 10th row. Okay, fine. But when I asked my 11-year-old, she's 12. I asked my 12-year-old, how many would each row have? She did this. Now I wrote it out, but she did this. She just started counting 14 by 2s. 14, 16, 18, 20, 22. This is the 5th row, 6th row, 7th row, 8th row, 9th row, 10th row. You see the problem? I used my fancy math and got 34. She counted and got 32. And one of us is right and one of us is wrong, and I'm a little bit scared to say I think it's my daughter who's correct, which is good for her, but bad for me. So what's going on? What seems to be going on is the difference between the way in which I write linear and the way in which we might represent an arithmetic sequence. So let's check this sequence out, right? This sequence right here is the one we just discussed. It's both linear and arithmetic. So we're still finding that those two things seem the same. The difference is this. When we deal with something linear, we assume that the first term isn't actually term number 1. We actually assume it's term 0, which is kind of strange. If I try to show it to you here, if we imagine that term 1 is in this space, term 2 is in this space, and term 3 is in this space, if we assume that this is linear, or if we're going to write it in slope-intercept form like we've done up to this point, we would start the 14 at term 0. If we're dealing with something arithmetic, we literally just shift this over, and the 14 is the first term, which makes a lot more sense because I could look in this arena if we were there and count the seats and get to 14, and then like my daughter did, just advance on by 4. In a graph, it looks a little different as well. If we were to compare these two things on a graph, you would find that the red thing here, linear, starts at the y-intercept. It starts when x is 0, so it assumes that the first number is your 0th term. That's kind of a strange one, but 0 term, or the 0 term. When we deal with something that is arithmetic, we assume that the first term is, well, the first term. And that's going to not really change the fact that one is linear or the other. You notice they're both linear. They're both going to follow a same straight path, but you're going to find that the equations are not going to match up. So for arithmetic, we write a different sort of equation. We don't write slope-intercept, we write something different. So let's check out the 2 different ways we can write patterns that are arithmetic. The first one is an explicit or direct formula. This is the gold standard of all the equations because it gives you the opportunity to jump ahead to any point in the sequence and calculate the exact value at that point. And you can do it very, very quickly. You can do it directly, which is the reason why we often call these direct or explicit formulas. Let's check it out. An explicit formula is this. Any sequence, if we want to determine the nth value, meaning some value in the sequence, here's what we do. We write the starting value. So in our example, we started with 14 seats. We determine the difference between each step, the difference between the intervals. And then we go ahead and we take one interval off. So if we're looking for the 10th row, we actually only calculate the 9 increases as we go because we're starting at the first one, so we have 9 increases, and that would give us our 10th one. So you always have one less. So you notice what we have. We have our starting value, which is whatever you begin with. We have one less than whatever you're after, and we never know what you're after, so we just always write n minus 1, and then the difference is over here is, in our case, 2. This could be negative if we were decreasing by something, but this case we were going up, so we made it a positive 2. On the other side is a recursive formula, and a recursive is simply you have to go one after the other after the other. So if we knew the 9th row of seats, we could calculate the 10th by just adding 2. Here's how we write it. We start over here. Where do we go here? So we don't have a starting value in the equation itself. We have the starting value. Oh, I made a mistake and I just wrote the wrong number. That was supposed to be a 14. We have the starting value off to the side. So we still identify where the thing begins. We just do it, well, kind of after this semicolon here. We do the previous statement. There's that n minus 1 again. So n minus 1, you're going to see that a couple different ways. And then the difference is represented. So ultimately, all we're doing here is saying if I knew the previous one, I could just add 2 onto it, and we would have our answer. And oh, by the way, we started at 14. So recursive is fine. Recursive is good. Recursive is something that, I don't know, could be valuable, but you need to know some stuff first. Explicit or direct is going to be much faster. Now, there's one more thing that I want to share in this in this little section of our unit is what an arithmetic mean is. Again, get away from calling it arithmetic. That's not what this is. This is an arithmetic mean, and the arithmetic mean is exactly what this would sound like. It's simply the mean of 2 numbers, or the number that's exactly in between 2 others. So let's go ahead and use the arithmetic mean to calculate a couple things. Find the missing term in each arithmetic sequence. I see arithmetic, so I know I can use the arithmetic mean. Here's what I want to identify. I want to know the number exactly in between 20 and 8. So one option would be just take 20 plus 8 and divide it by 2. That would give me the number exactly in between. 28 divided by 2 is 14, so I could put a 14 in here. For the sake of argument, though, what if I had more than one gap? Instead of just one space, I have multiple spaces. I'm going to use a slightly different strategy. Here's what I'm going to do. I see that from 14 to 2 is a decrease of 12. And because it's arithmetic, that decrease is the same each time. That's what's kind of key here. But I also noticed that there's going to be 1, 2, 3, 4 decreases. So I need to have those 4 decreases be the same amount each time, and for a total change of 12. So you can probably guess with me, you're going to take your negative 12 divided by 4 changes, and that means our D, or the value that it changes by each time, is going to be 3. So I could simply decrease 14 by 3, and by 3 again, and by 3 again, and then I would have my filled in box. So I could use the arithmetic mean a couple different ways. So 2 last questions. First, find the 15th term in this sequence. Now, right away, this doesn't really suggest a formula to me, so I'm thinking it's recursive. It's also telling me that I have a sequence called B, and the 14th term in the sequence is number 19. So the 14th term is 19. I'm changing by positive 10 each time. That means I'm going up by 10 every time. So if I'm looking for the 15th term, let's be clear, that's just B to the 15. That's just one more. So 10 added on to 19 is going to simply be 29, and I'm done, right? That's very, very easy. That's a recursive pattern. A little bit harder is this guy down here. Find the 52nd term of 11, 6, 1, -4, and -9. And for this, I don't want to have to just write them all out for 52 terms. So I'm going to create an equation. I'm going to make it an explicit equation, and I'm going to say a to the n equals, let's see, we begin with 11, and we decrease by 5 each time, and I'm going to go n minus 1. So this is my formula, right? So I'm starting here, I'm decreasing by this, and this is how many terms I need to decrease by. So a to the 52nd is 11 minus 5 to the 52nd minus 1. So this is going to be 11 minus 5 to the times 51. So this is 11 minus 255. So this is going to be, throw some equal signs in there, it's going to be equals negative 244. So there we go. So the 52nd term is going to be negative 242. I think I said 4 by accident. It's negative 244. All right, so there we go, negative 244. So the idea is a recursive formula works really well if you know where you're at and where you need to be, and it's pretty close. Direct or explicit formulas work much better if you have to extend your pattern far into the future.